Hello, hello everyone. Welcome to episode number 25 of this Amiga programming series in 68,000 assembly programming. Programming the Amiga the hardware way, not using the OS in assembly. I start, as always, to thank Fabio Ciucci for um, being so kind to let me do this stream on his book, and for giving me this possibility to using his book and be out there and sharing it with you. Okay, so the book now is we're going to start another part of the book related to sprites. Okay, and this time, so let me switch to the book because you are on the Amiga. It needs to refresh. There you go. So we are going to talk about how to access the sprites directly using the registers without accessing them using the DMA. Okay, before we were accessing the sprites using, let's say we created the data, and then we just pointed the sprite pointers to our data where the sprite was, and it was displayed on the screen. But there's another way of doing this, and that is by accessing the sprite registers directly. When we were accessing the sprites using the sprite pointers, we were making use of the DMA. Okay, so the DMA, what it does is it takes our data and transfers it to the registers where sprites are for the Amiga. Now, we also know that using the hardware sprites, we always think that there's a limit of 8 in the Amiga. Of course, if you multiplex, you have more, but we were always told that the sprites needs to be one lower than the previous one. Okay, there has to be one line of difference. This is not the case if we use the sprites directly without DMA. So imagine, okay, what the DMA is. Imagine a postman. Okay, we tell the postman, we give the letter to the postman, and the postman takes it and delivers it to the letterbox where we want our letter to be posted, or to whom we are posting it. If we eliminate the postman and we deliver it personally, okay, that means we are jumping the DMA, okay, and we are going to use the registers directly ourselves. However, not using the DMA, things are a bit more complex, but gives us certain flexibility. Also, it has some advantages. Now, this what I'm going to discuss today is not something that you should be using every time. It's only when you think it's necessary. Else, use the normal hardware sprites. It doesn't make sense. It does require a lot more work. However, it has some advantages, like displaying the same sprite multiple times on the same raster line, which we could not do that before. Okay, and you cannot do that with DMA, or if you use DMA. So I'm going to say what this paragraph says in short. So far we have generated sprites using the sprite pointers. There is another method though, and it's not easy but can be useful. Okay, that's what he said in that paragraph. In this paragraph he's saying, when we display a sprite on the screen and set up the sprite pointers, there are some things that happen behind the scene. Okay, what really happens is we use hardware DMA, and the sprite data is handled by this DMA. Okay, we will cover, okay, DMA in more detail in a later chapter, which is chapter 8, the one after this one. We will cover DMA. It's not the full DMA thing, but we will go into more detail in relation to DMA. So not everything is there. DMA is very important to the Amiga, so don't think that, oh, we can do without DMA. DMA on the Amiga is a very important thing, and you need to know how to use DMA. Okay? For now, we just need to know or understand DMA and how it is used within sprites, and how we do not need to use it for this method that I'm going to talk about, because we are accessing the sprite registers directly now. Okay, while before it was through a pointer, and the pointer just grabs our data with all the data that we supply and pass it to the DMA. So he takes the thing again, as I mentioned, the postman, which I got it from him, to be honest, but he talks about the postman delivering the letter. Okay, so we skip the part of the postman and we deliver the letter ourselves. The use, when we deliver the letter ourselves directly, and skipping using DMA is like, as I said, posting the letter in person instead of the postman. So what is the advantage of this when it's practically the same? Because we are just delivering it ourselves instead of DMA. What advantages to them? In terms of us delivering it, okay, it's the same process. There is no advantage to that, okay? But it gives us flexibility which we do not have when we are using the sprite pointers. It gives us the flexibility of creating some nice effect, creating more than one sprite, etc, etc, etc. But there's a cost to this. It's more work, and of course it's more intensive in terms of cycles for the Amiga, in terms of not just memory. Well, memory it's not that much, and you will see why in a minute. But in terms of you know, our couple list will grow quite substantially. So we have that issue. So this is where it all happens. This paragraph says it all. Okay, there are 4 sprite registers. Okay, let's see if it lets me select them. I just have this problem. Anyway, it's these 4 here that I am okay, all of a sudden it turned. Those 4. Okay, so we have 4 registers, and you notice that in the middle of each register there is an X that is replaced with the sprite number. So each sprite, we have 8 sprites, 8 hardware sprites. We put a number there, whether it's sprite 0 to sprite 7. Okay, sprite pause is where we specify the horizontal position of the sprite. We do not specify the vertical position using these registers. I will come to that in a minute. Sprite CTL, or sprite control, because that's what it stands for, is the the control word where we specify, okay, whether the sprite horizontally is moving 2 pixels at a time or 1 pixel at a time, and where we specify whether it's an attached sprite or not. Sprite date.a and sprite.b, okay, they are our sprite data. You remember, to form a sprite, we were passing the data, the format, remember, each sprite is 4 colors, okay? We were passing the data into 2 words. Each line of the sprite was made of 2 words, so that we can have 4 colors. Now, as I said, we have 4 registers, and each sprite has got 4 of these. I'm going to show you this, okay, and where they are. Yeah. So they start at 140, okay, and if you notice, these 4 are for the first sprite 0, and you see there's a 0 in the middle, and position control data A, data B, okay? I mean, data is for the images, they say here, okay? Again, sprite 1 has got 4 registers, and it continues like this till we arrive to sprite 7, where we have 4 sprites. Where we have the 4 registers for sprite 7. Same thing. Now, Fabio shows us, let's go back to the book. Fabio shows us that it's quite easy how to calculate the number instead of remembering all these numbers, from 140 to, I forgot what it was, 170, I think, or 17E, sorry. You can do this, okay? So we know that they start at 140 till 146 for sprite 0. We put x where x is the sprite number, whether it's 0 to 7, okay? And then we multiply that by 8, and we add it to the base address, okay? And we get the register. So this is quite a handy way of how we can access the registers. So I already spoke about this, but now I'm going to be maybe a bit in more detail, okay? Sprite.a and sprite.b, okay, are the data of the sprites that we are used to define, okay? As I said, I explained this. The sprite data is what defines the sprite, what is the sprite, or how the sprite is. We know, okay, from the previous ways that we were handling sprites, okay, that we had vstart, hstart, vstop, and the special byte, okay? Now, vstop, I said, we do not use, and vstart and vstop, so vertical is not used. We only use hstart, okay? And hstart is positioned in the low byte of um, S, SPR pause. Okay. So we also know that for the horizontal position we use 9 bits, not 8 bits. Okay. Bit 0, so from 0 to 8. Bit 0 is in the special register, okay? Is in the special register when we are defining the sprite. In this case, bit 0 is in the control register in the CTL, okay? The other 8 bits, okay, from 1 to 8, okay, are in VPOS. Sorry, are in SPR pos, okay? Whatever that's the sprite number is. The vertical position of how we specify the vertical position, it's a bit more complex. Not complex, actually it's not. It's just that you need to get your head around it. Because actually it's not complex at all. We have already done it many times and we didn't even realize. Um, but I will show in a second what it is. To see a sprite on the screen, it needs to be activated. Okay? You activate a sprite on the screen by writing to SPR dot. Okay? An example is going to follow where I show you, I'll explain all the data on the screen. I will explain the code basically, but for now just bear with me. Okay? So we activate a sprite by writing some data, something to SPR dot A. Okay? However, remember that A and that B are what represent one line of a sprite. Okay, so we need to populate each raster line. Okay, we need to populate the data. We need to pass the data. Remember, now we are doing it, not the DMA. We need to pass each data for each in this register, okay, in these registers that A and that B for each raster line, and we need a way of doing that, which I will show you. Okay, so don't panic. Okay, so if you haven't understood this, please give me a shout out here, and I can explain it. Um, it's not difficult. You just need to get your head around it. No, um, it it's not um, the end. It's not that difficult in terms of. It's just the concept. Just to see my notes here. So point one, I wrote we are populating the data in sprite.a and sprite.b, of course. The vertical position is done using couple list. Okay, we did not need to specify vstart and vstop. We did not need to because it's done using couple list, using the copper. Line 24, okay, we disabled the sprite by writing 0. So those were the 4 most important points for me when I wrote it down, okay, when I took my notes. As you can see, doing this via copper is painful, especially if the sprites are long. Yeah, if you have a long sprite, okay, let's say 200 lines, you need to specify that 200 times, and that can be painful. Now, there are programs that help you in doing this, okay? I haven't looked them up, but I know that there are. It's not something that you will use every day also, so don't you don't need to overdo it. When you cross the line, you just look it up and see what there is. um, but there are programs. Know that there are programs. I don't think Fabio not I don't think, so far Fabio hasn't mentioned any programs, um, but I know that there are that can help you in doing this. Now, suppose we want to display a sprite that has everything on the same line, like a column, okay? So this is the case of Flappy Birds, okay? Fabio did not know about Flappy Birds. I mean, Flappy Birds did not come out in, as far as I know, in 1994, okay? The concept came after. But he is saying using this method to draw a column, okay? So how do we do this? And now you're going to see how easy it is and how better it is also, instead of having to do the data, uh, the sprite data, as we were doing it for for such a thing, designing the column, you know, of a sprite, uh, and then passing it to the Amiga. Notice, first thing, same as before, we wait at line 40, okay? Raster line 40. Then we specify the position 80. Then we pass 00 to the control register. We always initialize it, okay? Then we pass E7 to dot B, okay? Not E7, sorry, OE70, okay, to dot B. Then we pass, and with this is when the sprite starts. Then we pass O3CO to dot A. We do nothing else. That's all that there is to do. When we arrive at the end of our sprite where we want it to finish, so line 60, okay, we write, okay, 0 to the control register, okay, and that is it. Notice how short this code is compared to specifying this sprite data that we normally do. I hope this explains or clarifies it better why this feature is a good thing to have and to know about. Let me see if I have any notes here. No, I set them all. So we pass here. So if this sprite, if this sprite displaying this column was 100 lines high, imagine how many data we are saving, and I already covered this in a way, okay? So this is if we had to use the normal way of defining a sprite, and this is the sprite that is 100 raster lines high, okay? So look how long this is and how much data this is occupying. Now the same thing, okay, but using the method accessing the hardware registers directly of the sprites without DMA. That makes a big difference on a system that is limited with memory. When you need chip mem, this might save you. So we go to the examples. Let's jump to the Amiga. So let's see this example, okay? Remember, this is the first example related to accessing the sprites directly. And there is our first example. As you see, we have two sprites. Those are two sprites. If I recall perfectly, that is the same sprite, sprite 0 being used more than once. They are not on the same horizontal line because we haven't covered that yet. However, notice also that one is wider than the other one. So one is 8 pixels, the other one is 16 pixels. Notice also that the pattern repeats, okay, from top to bottom for the same sprite. So this is what I was talking about, creating columns using such a thing. Okay, I'm pretty sure that there are people here on the stream that are thinking of how easy it is to do a Flappy Bird now using this technique, and it doesn't require a lot of memory neither. So it's also a trick that this was used in demos that were, I don't know, 4K demos for the Amiga, where you can create certain number of colors using the sprites and using this technique. Later on, you're going to see these sprites moving across the screen, and then you understand better what I mean by the demo that I'm mentioning that I have in my head, because right now you cannot visualize it. So let's go to the book. And now we have to switch to the exercises book. While I'm at it, okay, so I've told you many times to download the sources and to try them out of the book, okay, and the book is on two floppies, and it has all the chapters and all the exercises. The book has other things, okay, trust me, there is enough information to create another book from what there is on those floppies, okay. Fabio just doesn't cover it. So if I were you, I will look at those floppies. So let's see the first example. Now, the first example doesn't have any code to show you. It's just sprite data, which is a part of the couple list, which I'm going to show. Okay, this is the extra part in the couple list. Okay, and as you can see, I used two colors. One is the first sprite, and the other one is the other sprite. And what does he do? What he showed us in the book. Okay, we wait for raster line 40. We put this sprite, the first sprite, at position 80. Okay, we initialize the control register to 0. We initialize the .b register with OE70. Then we initialize the sprite data .a, sorry, with O3CO, okay, and then we wait till raster line 60 and we disable the sprite. On the same line, okay, and now think, okay, why on the same line? Sorry, I was going to confuse you. On line 140, okay, we put 80 into sprite pos. Okay, so we are defining the same sprite 0, okay, into another position on the screen. We are initializing the sprite.b, okay, register 46, and this time we do not need to specify the sprite control register, okay, because it was already initialized, so we know it was at 0. We have it here also when we switch the sprite. So all we need to do is wait for line 80. Okay, so notice what happened here. This is where I was going to confuse you, but as soon as the sprite was turned off, okay, we started initializing for the second sprite, but we set the wait at 80. Okay, so the other one finished at 60. This one is going to start at line 80. In the meantime, we set up the sprite data. Why waste time? Okay, when we arrived at line 80, okay, we just put the data for the sprite.a in the dot register. Okay, as you see, we have the column is 16 bits wide. Okay, and we wait till we reach before. Okay, when we reached before, we switch the sprite off, and that is why we have two sprites. By the way, the position is AO. Okay, so one is at 80 and the other one is at AO. Okay, so that's why you also see them shifted. One is more to the right than the other. I'm going to check my notes to see. Yes, notice that no height was specified. The height was specified with when we ended up at line 60. Okay, so no v-stop. In a way, we have v-stop, but not really. I have notes here where I said, but I'm just going to go through each point. Sprite pos was set before. Sprite.b was set before. We waited for line 80. We activated the sprite. We waited for line before, and we disabled the sprite. Okay, those were the steps that we did there. As you have seen, when we write directly to the registers without using DMA, we can still use sprites. Okay, and we still have access to sprites. We still have the same features that we had before. It just becomes a bit more complex. This paragraph should be in the book, in the theory book, okay, but he wrote it here. So there are some things he forgot to mention, I think, and he wrote them here. In the sprite control register, there are two bits that are important to us. It's bit 0 and bit 7. Bit 0 already mentioned, that says whether we are moving the sprite every pixel or not. Okay, so if that's a 1, then we are moving, the sprite is moving every pixel. If it's a 0, it's moving every 2 pixels. Bit 7, it indicates whether the sprites are attached or not. So remember, sprites are pairs. So sprite 0 and sprite 1, it means that they are attached sprite, and that gives us 16 colors. The last example that he shows related to this is an attached sprite of 16 colors. He says it is not easy to use the sprite registers directly. Okay, we realize that. In fact, most of the time these are not used at all. One of the advantages that I said that they have is when they repeat themselves, and like that we save memory. There is another advantage which we will cover in a minute, but that's the main things. So, in summary, to write sprites, to access sprites directly on the screen, we uh, we write the values in sprite pos, sprite control, and sprite b. That's the first thing we do. Then we wait for a y position in the copper using the copper. Then we write to sprite dot a. Okay. Then we wait for where we want the sprite to end, and we write at 0 in the sprite control register. That summary, I've repeated this several times now, so you should get the sequence of how it is done. But that was example number 1. So let's do example number 2. We go back to the Amiga. And this is the demo effect that I was talking about. Now, I tell you which demo effect I'm talking about, and you will immediately notice. Normally, you had lots of horizontal copper bars changing color, and like cycling from bottom to top or from top to bottom and vice versa. But then you would have vertical copper bars like these two. Instead of having 2, you either had 4 or 8. And you also had lots of colors. Why lots of colors? Because they were changing the colors using the copper list, which we will see in a minute. So you can change the color of these sprites every raster line anyway, so you can do it on sprites, the same thing. And that's how they were creating that effect. But that is when you saw pipes going horizontally and pipes going vertically. One were copper bars and the other were sprites using this technique. Or at least I believe that they were using this technique, because I've never disassembled one, but I know it is something like this. So I'm going to leave this running around and we jump back to the book. Now this shows also that Fabio was a demo coder, because he would not have thought about showing this this example, okay? So what do we have here? And I'm just going to start a bit from the bottom. Just notice that we have a routine move sprite, which we've seen before, and you're going to recognize it soon. But for now, I'm just going to go a bit further down. So to move these sprites, okay, here we have the data of our sprites, okay, the 2 sprites that you see there. We are writing, okay, at these locations, okay. where we see bar 1 and bar 2, okay? And we are writing the position, okay, for bar 1, okay? Remember, it's 140, register 140. The first byte is not used, the second byte is used, and this is where the position is, okay? So this is where we tell the sprite where it has to be horizontally. Here is we write 0, okay? I mean, we update that actually. Its register is the control register, okay, where we initialize to 0 and where we write 0 to end the sprite. Now, because the sprite is using the full screen, we do not need to write 0, okay? So we do not need to write to the control register in this case because we are using the full screen. So that is also something that we save. Like we did for the first sprite, we do it for the second sprite, but notice that in between, okay, we are initializing registers, okay? So register 146 sprite 0.b and 144 sprite 0.a, okay? So here is the horizontal and sprite control, and here is the .a, .b, and .a. When we do .a, boom, the sprite is displayed. We do the same thing for sprite 1, okay? Remember, we are updating this, okay? This byte is where we are updating stuff to move it horizontally. So I'm not talking about that, but I'm just explaining the data how it is. I know it looks a bit far-fetched, the data, but notice sometimes there's defined constant word and sometimes there is defined constant byte. That's because we need to write in the second byte of or first byte of the word, okay? That is why. So notice that sprite 1 pause, okay, and then we're specifying where we want sprite 1 pause, okay? At the end, we are activating the sprite, okay? We are writing to sprite.a, as you can see here. And this is a bug. That comma did 0, db0 is a bug that should not be there. But we are writing at register 146 the ff0, okay? Because the sprite, we are not updating it every line, it's repeating itself. So it creates this column as it is. So now that you know how the data is and we are going to pass parameters here, okay, let's talk about what's happening up here. So we have those sprites moving across the screen, but we are not doing anything special there. I tell you why. This routine, I have already covered it several times. We have a table where we read the x coordinates from. There is an offset for each sprite. One starts at table x minus 2 and the other one starts at table x plus 40 minus 2. In reality, is table x is at 0 position and and the other one is at 40. It's because it's accounting for what happens in the beginning. Because of that, okay, these sprites are they are using the same table, but they are at a distance, and they create what you are seeing, this effect, one following the other, okay? The other stuff is the routine where we are just updating the X position of a sprite, which is actually it's not a sprite. We are just updating a byte somewhere in memory using the table that we have here, and that byte in memory happens to be this address here where bar1 is. Okay, later on he mentions from which example we used is this routine, but I don't know if he mentions it here too. No, but he says in which when we covered it before. So now he suggests, okay, to do this. Okay, basically what this couple is to add this to the couple list. What this do? Okay, it gives colors to the bars. Okay, right now they are repeating themselves, but the colors are the default that we have. Where are they? Here. Okay, it's using these three colors, the sprites. But look what's going to happen when we add these. We specify at what line we want to wait for, and then we change the color, and we do it at several positions. So I'm just going to jump to the Amiga and show you that. And as you can see, by magic the bars became more nicer. Okay, we have different shades. I mean, we could have added more colors, but those are the colors that Fabio suggested to add, and basically it creates that effect. There's nothing to explain in the code. It's what you see in the book. It's that couple list where we say we wait at a particular line and these are the colors. Then we wait at another line and these are the colors for the sprite. That's all that is happening, nothing else. So we jump back to the book. As you can see, we wait at line 54, we wait at line 68, we wait at line 70C, and it continues like this. We wait at line 90, okay, where it says everything gray. Okay, that's what it means. Let's continue with example number 3. Okay, so this example, actually I should show you the example before I explain it. So let's go back to the Amiga. And let's do the next example. Nothing spectacular, okay? Nothing spectacular in terms of what you see on the screen, but there's a lot to be said. It's the same sprite on the same line, okay? This is to show you that we can have a sprite on the same raster line, same sprite used more than once, okay? And on the same line. Now, before we were talking about the copper, okay, that can handle our vertical position, but the copper can also handle our horizontal position. So imagine if you tell it to wait at a y, but also at an x. Then when you wait at an x and you tell it to wait also on the same line, so let's say the first one was at position 10, actually 11, because you can only use odd positions in the horizontal position for the copper. Let's say it was position 11. Then you can tell it, okay, wait till we reach position, I don't know, 101. Okay, and then you do something else. So on the same line, we tell it to draw the same sprite basically. So we told it to wait at line 11, and we told it, okay, display our sprite. When you reach when you reach horizontal position number 101, then you can display the next sprite. But it is the copper horizontal position plus the sprite horizontal position. Okay, it's not just the copper horizontal position only, and you will see it in a minute. So let's jump to the book. And in here, it's also just a repetition of data. Okay, I'm just going to, as you see, because now, although the sprite repeats itself, because we have two on the same line for the same sprite, we have to do it per line. Okay, so what happens is this. Okay, I'm just going to skip this line for now, which is the first line. Okay, I'm just going to tell you what happens at line 41 instead of line 40. Okay, when we reach line 41, we tell it to wait, because it's more clear here the horizontal position, how it works. We tell it to wait at position 40. Okay, x horizontal position 7. Okay, and we set the horizontal position of the sprite at 60. Okay, so at this position we told it to be at 60. When we reach, okay, on the same line position 87, the same sprite, we told it that the position now is 80. So on the same line, through the copper, we waited for a particular position. We could have done it before, it doesn't matter. He just chose a location. Okay, you have to do it before before sprite pause. Okay, so remember we said 87. Okay, and this is 80. Of course 87 has to be after 60. Okay, because you need to have done it, this sprite. So there is some time in between, so that's why a sprite cannot be exactly next to the same sprite cannot be used exactly into the next position, but fairly close. Okay, so this is how we display the same sprite on the same line. I believe here it's much more clear than here. Okay, but we're going to jump up here. Okay, what have we done? When we reach line 40, line 40, okay, position 7 on the horizontal position 7, okay, we set the position of the sprite to be 60. We set the control to be 0. We set the data B to be E7, okay, and then we initialize the sprite at 03CO. Okay, when we reached position 4087, okay, so this is a copy of this now. Okay, we told it in register 140 in the sprite 0 pause, we inserted 80. So the lines that follow after this one, okay, if you notice, we just specify the sprite position and where we wait, but we need to do it for each raster line. If the sprite is tall 14 raster lines, then we need to do it 14 raster lines. You see, line 43, line 44, line 45, and it continues like this, okay, till the end of it. line for F. Okay, so it's 16 pixels high, 16 raster lines because we started at 40 and we end up at 4F. Okay, and that's when we write 0 to the sprite control register. Okay, I think that explains and makes it clear how we can have use the same sprite on the same raster line. Okay, let's continue. Let me see what note I wrote here. Yeah, so what he's saying here is, as you can see, you can wait at several positions on the same raster line and display the same sprite. You cannot draw the same sprite next to it, okay, so to itself. It's difficult, okay, but you can do it quite close. Normally what they do is they use two sprites, okay, and then they swap between one and the other, and actually you're going to see an example. So let me see if there's anything else that I need to say here. You see, this is the first value that we inserted as position 60, okay, for sprite pos, and then we inserted the second one, which is 80. He gave us another hint, which I'm going to show. So let's jump back to the Amiga, and I'll show you. 3.1. So it is the same sprite, but notice we change colors. Okay, we're just telling it. So we're just not just waiting on the copper. So we know we wait on the Y and then we wait on the X. When we wait on the X, we're also saying change the color for the sprite. Okay, change the colors for the sprite actually. So that's why you see them as green. Okay, and let's actually see the code. As you can see, when we wait for a line, we change the color for the sprite. So on line 41, we change the color for the sprite. So one is the orange one and the other one is the green one. Okay, and it continues this for each line, I think till 4F or whatever, whatever the height is. No, it's shorter. It's six pixels high, 6 raster lines. So yeah, that's all to it. Okay, so we will see number 4. Let's jump to the Amiga before I explain it and see number 4. Okay, this is what I was talking about. We have two sprites repeated, okay, across the whole screen. We have the first sprite starts here, ends somewhere here, and then the second one and ends here. Okay, so from here to here, it's two sprites. Okay, but then we tell it to wait, okay, we're telling it to wait, and then start again drawing these two sprites again next to each other. And like that, in a screen 320 width, which is 320, we are able to have 10 sprites, 5 of each. Sprite 0, I think he uses actually Sprite 6 and 7. We can have Sprite 6 and 7 next to each other and repeat it several times. Okay? Now, with this effect, with this, just think how we can, what advantage do we have here? So first of all, notice that to create those sprites, okay, with that pattern, that nice mountain scenery that he has, okay, that means on each raster line he is specifying the data in dot A and dot B, okay, for each raster line. 2, okay, sprites can give us, okay, another, let's say, depth to the screens. You know that we have dual playfield, so one screen in front of the other, but you can also use sprites and put them either between the screens, in front the screens, or behind the screens, and that gives us 3 layers. And if you divide, and if you use more, let's say here we are using 2, and if we use another 2, we can have another layer, and like that we create one layer after the other, and it's all done via sprites. So how he is doing this? Let's jump back to the book. Please note that there isn't much code in terms of how you define. We are just defining the sprites. We are not moving them. I mean, in this case, we are not moving them. Actually, the next example will be moving the sprite, but in terms of what he is specifying, we are not really doing much. So, first of all, notice this syntax. Okay, this is how in assembler terms you can specify constants to a label. Okay, you can either use equals or you can use the EQU. Later on in the book he's going to explain it, but I'm explaining it here because we have arrived into it and I thought I explain it. Basically, you can, instead of specifying 170, you can write sprite 6 pause, okay? And in fact, down here, he's using sprite 6 pause instead of register 170. That's all what he's doing. He just put a name, we just put a name to a number. As I said, you can either use equals or EQU, which is the same thing. The assembler is able to understand both. Notice that for each line, okay, we have a number of data, okay, but we are also setting the other registers, okay. So notice that we need to do it for sprite.a, sprite.b, okay, for both sprite 6 and sprite 7, okay, and we also need to specify this sprite position, okay, for both 6 and 7, okay. This is where we are waiting on the screen, and here it says line 50, which is line 50. In the horizontal position it's 25, okay, and this should, the second one should be the same, okay, third one is the same, okay, there is just the position. If you notice, where we are waiting, okay, for the sprite varies according to the line where we are. But the data is repetition for each line. Let me see if I wrote anything in the notes that I should be mentioning it. Maybe I should start from top. So this is, I explained that here. Here is where we set the sprites .a, .b, and sprite pause, okay, for both sprites. Yeah, it's a repetition of the same what we saw before, and it continues for each line. I believe the height of it is 14. So from line 50 to line 5D. Okay, then we tell it we should write zeros for the sprite. You see, 7.2 and 7a, we write zeros into them to end the sprite. So that is, okay, remember, each one of these is the two sprites next to each other. Then, so this, all of this is the two sprites next to each other on the same line, and then they are repeated. Okay, and we fill the data. What is the data? .b, .a, and .b. Here we have 0. Actually, the first line for .a is 0 for sprite A and sprite for sprite 6, but sprite 7 has got F0 and 0. Okay, and then line 51 .a is 001, .b is 0, 7 is B8, and 40, and it continues like this. So each line we're specifying the data, but remember, each sprite is also repeated across horizontally, and this is the repetition for the sprite. So basically we are immediately initializing the position for the sprite. Of course, this is the weight. Okay, so here we waited at 51.25, then we wait at 51.4b, 51.5b, 51.6b, 51.7b, and it continues like this throughout the line. Okay, and this is why so one how to say it, two sprites are actually from here, if it lets me select, till here, till here. Okay, that is the two sprites next to each other. Then we wait, and we have the next two sprites, which are happen to be the same, but this is how we display them till here. All we need to do is change the sprite position, okay, for both of them, and it continues like that for the same line. I hope that clears it up. So as I said, the screen is 320 pixels, so we are using sprite 6 and 7, and there are 10 sprites on the screen, so 5 each, 5 of 6, 5 of 7. He is explaining what I just explained. Okay, we wait, okay, for the line, then we have our initialization of the sprite.a and sprite.b, and then we change the position for them, and we wait on the line. Okay, the last part is the wait. Let's see if I set everything. We repeat this 10 times. Yeah, Um, yeah, so that's basically it. Let's do 7y5, but I believe between 7.4 and 7y5 there's something to read in the technical book. So between 7.4 and 7.5. Yeah. So we need to do this part. To be fair, this part is quite easy, okay? It's nothing special. He is saying what I just said earlier. You can create labels to 4 registers. Here he's using the EQU, but you can use the equal sign. And that's basically what he's saying here. So normally you have a file that defines the constant files, the constant your constants in the book, and you use that file to in the data. No, so you don't have to remember the numbers of the registers, but you need, but you can remember the labels. Here's, so you see here he's using EQU, here he's using the equal. Um, the routines are different, but it's just what counts. Okay, he's saying that everyone can understand both, so it doesn't make a difference. Also, labels end with a colon. Okay, some assemblers, actually I think you have the option to disable that. I prefer to have a colon at the end of a label. It's just me. But actually you can turn that off. It's an option in the assembler. Here he shows more options of how to use it in equal sign. So bytes per line, we have 40. Height is 256. So the space taken for 1 bit plane is the 40 times 256. Okay, and then he defines it in the bit plane size. Okay, define constant, define storage. Okay, but that's basically it. So we jump to the last example for this block of the book. So we are seeing the same thing that we saw before, that we had before, the scenery that we had, but this time it is scrolling. Now, we are not using hardware scroll here. We are using a very nice trick, okay? We are just rotating the pixels inside the sprite, which create this effect. That's why I told you you can create multiple layers using the sprites too, okay? I'm going to explain how we are doing it, but please note it's just shifting of bits from left to right, and what exits from the right goes back to the leftmost bit. Okay, so that's how we are doing it. I'm going to leave it there and go to the book. So basically I already explained it by telling you what trick he's using, but so this example I'm going to start a bit from the end of it, because you'll understand me better. So first of all, this is the same data that we had before. Okay, nothing changed. Okay, just note that between one here, between one and another, there are 44 bytes, if I remember correctly. Okay, so that is the difference what we need to add. If not, anyway, it's a number. Okay, let's put it this way. I think it was 44, but I cannot remember 100%. Okay, but it's the same data. We didn't change anything. Now, here is what's happening. Okay, I'm going to start from here. I was saying that the sprite data is being rotated. We have two sprites, okay, repeated several times on the same horizontal lines. So what Fabio is saying here is we have, remember, we have dot A and dot B for the sprite data. Okay, so here he's reading the first word. Okay, he's sorry, he's reading the first the first word of the sprite 7 dot, sorry, sprite 6 dot, and then and also that of sprite 7, we rotate it. Okay, we rotate to the right. Okay, so we shift the bits. Okay, what happens is what exits from the right hand side, okay, so bit 0, what goes out of bit 0 comes in at bit, because we are using word long, it comes at bit 32. Okay, so it's rotating. Okay, since we have two sprites, we combined, remember a sprite is 16 bits wide, but we combined that of sprite 6 and sprite 7, and we are rotating the bits basically. So we do it for sprite.a and we do it for sprite.b. Okay, so these two routines are identical. Okay, that's what I mean. It's a repetition of the same one, as you can see. Later on, he's going to show a diagram of ROR, how it really works, but it's just shifting of bits. Here is how height is the is our sprite. Okay, so we can see it's 14 raster lines or 14 pixels high, so we have to repeat this 14 times. Okay, and then loop it 14 times. So let's see, now he's going to explain. This we have already explained, okay, in the previous one. So now he's going to explain, and as you can see, here is when we switch off the sprites. Okay, same as before. So here he is explaining how ROR works. Okay, so imagine this number, okay, and funny enough, it ends with 101. Okay, and he's shifting it 3 times. Okay, so what's going to happen? The 101 goes to the back and everything else moves. So these, okay, are this, and what has exited came back in from the left hand side. In this case we have byte, but up there we were using long. Okay, so if I go further up, we were using long, so 32 bits. And why 32 bits? It's because we had two sprites. I will go back to the Amiga just to remind you what's happening. So remember, the pattern is made of two sprites, right? And this one here, okay, to the other one, because I need to keep up with them, it's actually one pattern. We are combining the two sprites together and we are shifting the bits. That's why if I show the previous example, okay, where we discussed it, how he achieved it. Okay, so a sprite 6 starts here, ends somewhere here, and then sprite 7 is still here. Okay, what we are doing is we're shifting a bit from here, okay, moving it here, and what we had here comes back here. And because we are rotating this, okay, it looks like they are moving, but actually they are not. It's just give the illusion. So we are rotating the sprites, the both sprites on themselves, and we are doing it for each one, for each couple, for each two of them, basically. Uh, okay, so that's how he is creating this illusion that we have a scroll, but actually we are just shifting the bits of the same sprite. So we have finished, okay, accessing the sprites using the registers directly without using the MA. Okay, you have seen, I need to switch you to the book. You have seen, okay, how, what is the advantage of using such method. It's much more painful, but it has some advantages of how we can do these. Now we arrive to the last part of this chapter, which is sprite animation. I mean, there isn't much. If you notice, he only has 2 paragraphs, so it's not that there is much to it. We have a sprite that is moving on the screen, and basically while it's moving we also change the frame, we change the sprite pattern. That's what we are doing. He is going to show this. I mean, before we were using animation, or so animation, using the sprite pointers, okay, and pointing to our data and then animating it by changing the sprite pointer. Now we're going to see it using the registers directly, okay, so no DMA involved. He is also going to attach the sprites, so the sprites will be 16 colors, where there's only one sprite, but it's animated. I will be showing the example in a minute. I'm just going to see that the notes that I have written, I've set them all basically. So every frame, okay, every vertical blank or wherever you want to wait on the screen to update your screen, you also update the sprite. Not just the position of it, the X and Y, but you also update what animation you want to display for that particular sprite. Um, that's basically it. That's basically it to it. So basically, I can show you the example. So if we jump to the Amiga, that's the example that we have. So I can tell you in advance, okay, we have already seen how to have a sprite on the screen and moving on the screen by reading data from a table. So the X and Y coordinates of how this sprite is moving are coming from a table, okay, which we are reading, okay. We are also using the universal sprite routine that we have discussed several times, where we pass the x and y to this routine, what is the height of our sprite and where our sprite is, okay, and we move it across in this on the screen. In this case, we are also updating the animation to see it rotating. Okay, so that's in a nutshell. And just to give you an idea that we have covered basically everything, uh, and you're going to see routines that we have already discussed and went through one by one. So we jump back to instead of the theory book, we jump to the example book. I had to explain that, yeah. So this is our example. We have, as you know, where I don't highlight, we have already covered. This is the init, let's say, and which we have discussed several times, init of how we take over this operating system and how we are having initializing these sprite pointers in this case. We have two routines, okay, which I'm going to show or discuss, but you're going to see that we have done them already. I'm just going to go from the bottom of it, okay, because down here we have our universal routine, which I have not highlighted because we have discussed it several times. But to remind you, okay, in 8.0 we have the address where the sprite is. In T0 we pass the y-axis, in the 1 we pass the x-axis, okay, and in the 2 we pass the height of the sprite, okay. You know this, so nothing nothing new. It's the same universal routine that we always used. Here we have the two tables. One is the y coordinate table and the other one is the x coordinate table that were generated using the cs or is command, okay, from the assembler. As in one or as in pro, they both have these commands, as you know, and I showed you how to use them. This table is made of 200 byte values, and this table is made of 150 word values because it's the x coordinate and it's using 9 bits. Okay, so we need word. Here, okay, is the position where we are in the table for the x and for the y. Okay, so when we read the next position, we are saying, we are storing which one we read last, okay, and we are storing that here and then increment, so it's just a pointer where we are in the table. This routine, okay, is our routine that reads the x and y, okay, and passes them to the universal routine, okay. So we have done this several times. It's the same routine, and we had this chapter, I think the first 3/4 of it, or let's say the first half of it, was just this routine and what we have below, okay. So we have discussed this. I'm going to jump a bit this. This is the routine that is updating the frames for the sprite, and I'm going to divide it into 3, okay. So the first part, there are 3 parts to it, the routine. Doesn't let me select sometimes. Okay, so there is this part. That's the first part. There is this part. Come on. From here to here. Okay, that's the second part. And then we have the last part. Okay, what remains. So 3 sections. Okay, what we have here is pointers to our frames, and I'm going to show you the sprite data now. So these are the frames for our sprite. Okay, everyone, so that's why I remembered 44. Every one of them is 44 bytes. Okay, because we are using attached sprites, then we have 2 together. Okay, so this is sprite 1, sprite 0, and this is sprite 1. Okay, but because all we need to remember is this, we don't need this. We know that the difference between this and this is 44, so it's easy to calculate it. What we do, and this is this routine, okay, so I'm just jumping back and I'm just going to remind you, okay, of this routine. Okay, remember when we had copper bars and we were shifting the copper bar, what the color at the bottom goes up, when it reaches the top goes again from the bottom, and we were cycling all the, it's the same routine. We are just rotating this, so 6 becomes 5 where 5 is, 5 becomes where 4 is, continues like this, 2 becomes where 1 is, and 1 goes to the bottom, and we rotate that. We just read the first one from the top, okay, and we pass the information to the routines down below. So I'm just going to skip now this part. Okay, I'm going to tell you what it is, but I'm just going to skip this part. Okay, and I'm just going to talk about this part, the second part. Okay, from LEA to here. This is the rotation of these. Okay, so what's at the bottom goes on top, and etc, etc. So it's the same part. This routine, we've seen it. I have a note where we've seen it, and I will tell you where we've used it. I just reminding you. So that's the rotation of it. This part is where we read where this is pointing and passing and setting the values for the routines below. Okay, to point the sprite which frame we are going to use. So nothing really, it's something that we've seen. Here the first part is, so you know that in PAL the frames are 50 frames per second. Okay, instead of having it, the animation happening every 50 frames per second, it's happening every 25 frames per second, I believe, either 25 or 18. I think it's 25 though, because we have we once we add 1 and it becomes 2, then we if it's 2, okay, then we don't do anything, but when it's not 2, then we update. So when it's 1, basically it's done. He could have used the negate instruction as before, but he used this method. It doesn't matter, it's 25 frames per second, okay, instead of 50, so that the animation doesn't look so fast. That's of the orange part in the middle of the ball, going around the screen. That's what it is. Let me see if I have a note from where I got it. I know that I have it somewhere in the notes, but this is the routine. Further down he's going to explain it, which I will go through. So I explained I explained the code, but now I'll go through his notes. So he's saying we have 6 frames for 6 animation frames for the ball, okay? And remember that the sprite is attached, so it's 16 colors because we are using two sprites. So that's what he says there. Yes, that's what I was looking for. That routine was covered in lesson 3E, okay? So we did it in chapter 3 when we were rotating copper bars, okay? And if you want to check it out, it's on video, it's on stream number 9 of English. Of course, the stream is not, I haven't put the stream yet on YouTube, but once it's on YouTube, you will see that number 9 is the stream that explains that routine, okay? And he is also mentioning it here. Actually, look, lesson 3E, okay? The LEA 44 is the distance, which I told you, from one to the other, because it's two sprites. We use them and to get the data of the second one, second attached sprite. So with sprite 0, sprite 1, we add 44. I believe that's it for this example. Let's go back to the theory book now. So first of all, this is what's coming next, okay? The book, as I said, was divided in two, okay? When he has done chapter 7, he released the book, but only half of it, okay? The second half is this part, okay? How to program the blitter, interrupts, audio, differences between 68020 and 68000, doing games, mathematical routines, 3D, AGA, how to optimize the code, and programming the graphic card Picasso, okay? So the book, the second, that's why I told you the book changes and it's more, the sources are a lot longer and it's more difficult, okay? So it's why it's important that you follow, have the book with you, basically. There's nothing else that he said there, it's just what he's going to cover. And I can tell you that chapter 8, okay, which is understanding better the 68000, the first part, we already covered it, is how to copy it, how to copy the resources to the hard drive, okay? So we will actually start from somewhere here, okay? So for today, we have basically finished. So thank you very much. Thanks for following, and I hope you enjoyed the stream of today, and have a good week. Thank you very much. Bye-bye.